Hey, this is Dr. B, and let's take a look at salts. These are known really as ionic compounds, and they always consist of a metal, meaning left of the staircase, bonded to a nonmetal, right of the staircase. The metals always prefer to lose electrons. Notice the positive charges here. The nonmetals gain electrons, and so we have a positive charge attracted to a negative charge, and that's the basis for that chemical bond. So here it is shown for an individual part, sodium chloride. And by part, I mean that although that is, sure, table salt sodium chloride, it's part of a giant lattice that looks like this. To melt it, you have to heat it up to 801 degrees Celsius. That's a lot of heat. And to break those bonds, they have to apply 787 kilojoules of per mole. That's for every 58.5 grams of stuff there. And that's a lot of energy as well. It's more proper since they're not just one bond per molecule here, but rather a continuous lattice to talk not about the bond energy, but rather the lattice energy. Therefore, we're talking about oppositely charged ions, but they're not individual molecules. You have to make out the unit for each one to figure out what its effective molecular weight is. Even though these bonds are so strong, you throw them in water and they dissolve. And this is shown diagrammatically here. Here's the sodium cation and the chloride anion after you throw it in water. And look at all those water molecules that have surrounded it. The basis for that, if you look at it in great detail, is that there's an attractive force that overcomes that bond energy, and that is, see all the oxygen atoms? Those are electronegative. They have a partial negative charge, and each one of them is attracted to the sodium cation. Notice how they flip around here, and you have the positively charged, I should say the partially positive charged hydrogen ions that are attracted to the chloride anion here, and this is sufficient to dissolve these molecules. Another way to look at it is to draw it chemically, which we're going to do here. Here's the chemical equation for table salt dissolving in water, which they do right there. Sodium chloride in the solid form like this, in the presence of water. There's your water molecules. Note that water is not acting as a reactant here, so we don't write it as such. We usually just draw it above the reaction arrow. Ionizes this substance into the sodium cation and the chloride anions, and they use this two-letter abbreviation AQ. That means it's now aqueous, dissolved in water. So that's the chemical equation for table salt dissolving in water. Not a typical equation because technically this is not a reaction. This is just the ionic compound dissolving. Another quick thing about ionic compounds, or salts if you will, if you smack them, you oftentimes get these cracks that form big straight lines, meaning they're brittle. The molecular sort of view of this is that when you have the lattice, you have a lot of attractive forces. Plus, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus. But all it takes is a sharp blow to frame shift this thing so that it goes from all attractive to all repulsive along this column. Plus, plus, minus, minus, plus, plus, on. And oftentimes you get straight line cracks for these salts. They're brittle. Naming them is not too hard. Let's take table salt. The cation is sodium. The anion is chloride. We all know that you do not call this chloride sodium, so we've learned something. We always begin with the cation and then the anion, and this is named sodium chloride. The charges, as you might know, are +1. Here it is for sodium, and -1. There it is for chlorine. And we simply take the IDE at the end, and we say the INE of chlorine and make it sodium chloride. The charges are +1 and -1, which is a nice match, and therefore NaCl is a nice uncharged compound, +1 and -1. That's not always the case. Let's take magnesium fluoride. We would not say fluoride of magnesium. We would not say magnesium fluorine. Most people from conversational language know to call this magnesium fluoride. But the charges are not always plus and -1. Magnesium, it's a +2 ion. Fluoride, it's a -1 anion. This does not make sense in and of itself. Salts are always uncharged. Write that down if you need to. Therefore, this would have a +1 charge. By logic, you might be able to imagine that we would need 2 fluoride ions for each magnesium cation to offset this. And that would be right. It's MgF2. You can go through that thought process each time, or you can simply say, let's switch the charge numbers. Let's put the 2 there. Let's put the 1 there. That's a nice shortcut for coming up with the formula, which is MgF2. Note, by the way, that we do not say magnesium difluoride. For these ionic compounds, you drop the monos and dis for these anions, and we simply call this magnesium fluoride. Here's some properties of ionic bonds, a little bit about ionic compounds and how to name them.